way to approach that mathematical operation. And so the operation that I'm talking about is division, okay? So we're going to just review, Jonathan, not from last week or the week before, but we're going to review long division and then look at another way to perform division when working with polynomials. So if I look at long division, and I think back to when I first did long division, I looked at, we have to understand the names of the components of a division problem. So the dividend is the number inside the root, the division sign. The divisor is what you are dividing by, and then the result of actually performing the division yields the quotient. Now, you may or may not have a remainder, and we'll talk about how to deal with that. So if you think back to way back when we first learned how to do arithmetic and division, in particular long division, I could go ahead and say, all right, let me rewrite this expression and check my answer. So what would be my dividend? 124. And what would be my divisor? 4. And so I would perform my long division, and you're laughing, but you know, this is important. What number would be, 4 goes into 12 how many times? 3. So that would give me 12, and I'd subtract, and then I'd bring the 4 down. And I'm doing this with just constants because these will become polynomials in a minute. So that's why we're reviewing this. So then if I then ask myself, 4 goes into 4 once. Okay, so my quotient, my result is 31, because if I did this, I would get 0 as my remainder, because it divides evenly into it. So if I wanted to rewrite this in this notation, I could say, all right, the dividend was 124. The divisor was 4. The quotient was 31, and my remainder was 0. So if I were to think about a mathematical operation, the dividend equals the divisor times the quotient plus if there were any remainder. So we should be familiar with these terms. We should be able to represent this operation either as division, long division, or as an equation showing all the components. So again, if I were to rewrite this problem using long division, my divisor is now 5. So if I actually did the division, 5 goes into 12 how many times? 3 times? No. 2 times. Then I'd subtract, bring that down, and ask myself, 5 goes into 24 how many times? 4. Okay, and then I do the multiplication, and then I do the subtraction. So then I'd have a quotient of 24 with a remainder of 4. So if I wanted to write that as a mixed number, how would I write that as a mixed number? 24 and 4/5. Could I write that as an improper fraction as well? Yes, I could, right? And how do we write that as an improper fraction? Do you remember? Oh, 24 times 5 plus 4 is what? 124 divided by 5, which is really what we started with, right? So improper fractions, fractions are ratios, ratios are fractions, so they're division. Okay, and again, I could rewrite this. The dividend equals the divisor times the quotient plus the remainder, and it works. Now, that's great. That's when we have a constant divided by a constant. But what happens now if I actually have polynomial expressions divided by yet another polynomial expression? Well, let's look and see what we're working with. This first polynomial can be classified how? What is that? Remember, we classify polynomial expressions based on the degree and the number of terms. What is that? Okay, and what's a term we use to describe polynomials that are second degree?
Quadratic.
Quadratic, right? This is a quadratic trinomial. So this is a quadratic trinomial, and it is divisible by what? Dividing by what? Okay, which is what classified as? And be more specific. And what do we call first degree? Linear, right? Oh my gosh, here's our review, Jonathan. Yeah. All right, so we have a quadratic trinomial divided by a linear binomial, okay? So I'm going to set it up as long division. So then that would make me ask myself, what is the dividend? And you would say the dividend is what? And the divisor, what I'm dividing by is, okay. And so now I'm going to perform long division. Now, a little hint to help you not get thrown off and make huge mistakes is to make sure that you have all powers of x represented in each expression. This will allow you to maybe have less room for error. So in other words, I have x in my dividend, x squared plus 10x to the first plus 21x to the 0 power. Technically, all powers of x are accounted for. My divisor, what I'm dividing by, is x to the first plus 3x to the 0 power. So I'm good to go there. Miles and Ash, cover your noses. So if I were to perform division, I'm going through the same process. But what I'm really looking at is I'm looking at this and I'm looking at that. And I'm asking myself, what am I multiplying by x to get x squared? That's what I'm asking myself to figure out the first term in my quotient. So what are you multiplying by x to get x squared? X. So since it is an x to the first power, I'm going to place it above the x to the first power in my dividend. Okay, now I'm just going to perform the multiplication like I did before. I'm multiplying x times x, which is going to give me my x squared, and I'm multiplying x by 3, which is going to give me a plus 3x. Write it out as an expression. It has to have a plus or a minus there. We're either adding or subtracting. I need to know the sign of each term. So do you see how I figured out, number one, what I'm multiplying by, where to place it, and then performing the multiplication? Yes, so far so good. Now, what am I doing with those? I am subtracting. Get in the habit of showing the subtraction. As you increase the number of terms that you're manipulating, and you're adding, or in this case, subtracting from like terms, if you do not put the minus sign there and you don't show that I'm subtracting each of these terms from their corresponding like terms, bless you, you are going to make an error. It is inevitable, so please be careful. So now let's do the subtraction. So I have x squared minus x squared. I'm doing the subtraction here. X squared minus x squared. What is that going to give me? 0. Then I'm doing 10x minus 3x. What is that going to give me? 7x. Ugh. 7x. So I have 7x, and then I'm going to bring down my plus 21. Now I'm going to go through the same process. I am now going to ask myself, all right, what am I multiplying by x to get 7x? And you would say a plus 7. Make sure these stay expressions, polynomials, plus or minus. So I'm asking myself, what am I multiplying by x to get 7x? I put it over my constant. Now I'm going to do my multiplication. 7 times x gives me 7x. 7 times 3 gives me a positive 21. I am subtracting. 7x minus 7x. 0. 21 minus 21? 0. So my remainder is 0. So what is my answer? My answer, my quotient is this. So the answer to this problem is the quotient x plus 7. Again, I could rewrite this in this dividend. Oops, what did happen here? I could rewrite this in my, what happened? Why is it not grouped? I don't know if that's the one that groups it. We'll see. Oh my gosh, it just, heaven help me. I could rewrite this in this form, right? So this form is dividend. My dividend is x squared plus 10x plus 21. That equals my divisor times my quotient plus my remainder. So if I FOIL those two, if I multiply this by this, I'm going to get this. Am I not? That's beautiful. That's beautiful. That's beautiful. So mine actually went to this next page. Okay, so let's go ahead and try the next. Well, no, we're going to skip the next one. We're going to do this one afterwards. So I'm going to save this. This one is for you as an exercise. Let's look at number 5, because I want to get through this and synthetic division before we leave today. So if I were to represent this in terms of long division, it would be, give myself some space. My dividend, x squared plus 10x plus 21. All powers of x accounted for, right? And it's written in standard form. I am dividing by, I have 0x to the first, right? So I put a placeholder. You don't have to, it helps. You don't have to. So what am I looking at to help me decide my multiplication? Well, I'm looking at this and I'm looking at this and I'm asking myself, what do I have to multiply by x squared to get x squared? And you would say 1. Ooh. 1 is a constant. I'm putting it there. And then I'm performing the multiplication. 1 times x squared is x squared. 1 times 0x is 0x. And then 1 times 7. Do you see why I put that placeholder there? So that I can make sure that I align like powers of x so that I can combine like terms. Now, keeping in mind that I am subtracting, x squared minus x squared, gone. 10x minus 0x gives me 10x, and then 21 minus 7, positive 14. So how would I represent this answer? Well, technically, this is 1 plus 10x plus 14 over x squared plus 7. Right? Because this is my remainder over, right? Actually, I don't want that. But let's put it in this form where I have my divisor, or actually my dividend equals my divisor times my quotient plus my remainder. So I have x squared plus 10x plus 21 equals x squared plus 7 times 1 plus 10x plus 14. Does that work? Yes, because this is x squared plus 7 plus 10x plus 14. Something went wrong. No, it didn't. X squared plus 10x plus, ooh, look, hee hee hee, how cute is that? All right, let's try another one, shall we? Ooh, look at those powers of x. Okay, let's set it up. what's the first thing I want to do is I want to check my expression, see if I have any missing powers of x, make sure that I've written them in standard form, put in any placeholders that I need. So my dividend, 2x to the 5th minus 8x to the 4th plus 2x cubed plus x squared. If you want to put a 0x and a 0, go for it. Now, what am I dividing by? I'm dividing by 2. My divisor is 2x cubed plus 0x squared plus 0x plus 1. Do you see my placeholders? Okay, now to do the division, I'm saying, okay, what do I multiply by this to get this? And you would say x squared. So where am I putting that? Right above the x squared term. Then I'm going to distribute, multiply. So 2x cubed times x squared is, okay, x squared times 0x squared, 0x to the 4th, right? Plus 0x cubed plus x squared. All I did is multiply. Now, I'm reminding myself that I'm subtracting each of those like terms that I just found. Each of those terms from their like terms in the original dividend. Let's do the subtraction. First one's gone. Negative 8x to the 4th minus 0x to the 4th. X squared minus x squared, gone. So you might want to put a 0x squared, right? Now look what I'm doing. I'm looking at this term again and asking myself, what am I multiplying by 2x cubed to get negative 8x to the 4th? And what am I doing?
Multiply by negative
4x. Negative 4x. Those placeholders are helpful, huh? So let's now do the multiplication. And what am I going to get? Negative what? Keep going. And again, I'm reminding myself I am subtracting because that subtraction is important. This is gone. What is the next term? Keep going. Plus 0x squared. Plus 4x. Minus a minus becomes plus. And I'm going to bring down that 0. Okay, so now I'm asking myself, oh, what am I multiplying this 2x cubed to get 2x cubed? And you would say positive 1. Look at that little quotient. Look at that little quotient. Let's see if we get a remainder. Let's do the distribution. And I'm going to get 2x cubed plus 0x squared plus 0x plus 1. Do the subtraction. And what do I get?
4x minus 1.
So in other words, this times this. I'm sorry, I said that backwards. This times this plus this should give me my original polynomial.
Is that how we would answer it on the test?
Well, your quotient would be this with a remainder. So x squared minus 4x plus 1 plus 4x minus 1 over 2x cubed plus 1. That's your entire answer.
Okay.
Right?
Yes.
which would correspond to like a mixed number. So similar to what we did up here, right? We okay with long division? Yeah, that's fun. That's exciting. Well, there's another type of division you can do, but it only works in special cases. But boy, when you can use it, I would use it. It is called synthetic division. So it's a shorthand, easy way to divide polynomials by only a linear binomial. So if your divisor is not a linear binomial, you can't use synthetic division. So the first thing you want to do is write your dividend in standard form, exponentially descending order, putting placeholders, you know, powers of x that are missing with a 0 coefficient. You have to do it with synthetic division. And then again, you can only divide by a linear binomial, x plus or minus a, because a could be plus or minus. So let's first look at these examples and say, oh, couldn't we even use synthetic division in these cases? Well, in the first instance, what am I dividing by? I can use it. What about the second one? Yes, I can. What about the third one? No, that is not a linear binomial, so I would not be able to use synthetic division once we know how to use it. I would not be able to use synthetic division on the third example because it's a quadratic binomial, and it can only be used for if you're dividing by a linear binomial. In this case, you'd have to use long division. So on the test next Monday, a week from today, if I give you this problem and I ask you to use synthetic division when you can, you would have to state it's not a linear binomial. I cannot divide on that third example, but you would then have to use long division. Okay? So in the instances where you are dividing by a linear binomial, you will be expected to do that. You will be expected to use synthetic division. If it's not possible, then you would have to say, I cannot use synthetic division because I'm not dividing by a linear binomial. So let's talk about what on earth is synthetic division. Oh, it's beautiful. So exciting. So exciting. Okay, here we go. First thing you want to do is check that your dividend is in standard form and not missing any powers of x. If so, we need to put placeholders. Okay, it's in standard form. It's not missing any powers of x. Let me ask you, what is the leading coefficient? Leading coefficient, 1. Okay. What you're going to do to set up to do synthetic division is you're going to write all the coefficients of your dividend. So what are my coefficients? 1, 10, 21. That's why if you are missing a power of x, you must put a 0, or your synthetic division is wrong. It just will be wrong. There's no way for it to be right. Okay? Now, my divisor, what I'm dividing by is x plus 3. Set that equal to 0 and solve for x. What is x? X is -3. So in a little tray, I'm going to put -3 because that's what I'm dividing by. Then I'm going to draw a little bar, and I'm going to perform synthetic division. So what is synthetic division? Well, you bring the first term down. So that's a 1. Then you multiply. What do you multiply? You multiply this times this, and you put it here. So 3 times -1 is, then you add. 10 plus -3 is, then you multiply again. -3 times 7, and you put that product here, which is, and then you add. Okay, now our coefficients of our dividend went here, right? I divided by this. So that means my result here is 1 degree less polynomial. So this is the coefficient of now x, and this is my coefficient, or x to the first, x to the 0. So I'm saying that this divided by this is x plus 7. That's my quotient. Is that true? Well, if I multiply my quotient by my divisor, I'm going to get my dividend. Now, we will see this is very useful because once we perform one iteration of this synthetic division, I get a lower degree polynomial. So I'm now working with a lower degree polynomial, which may be factorable, which may be easy to find the values of x if this were embedded in an equation. Let's try another example. Again, I look to make sure that my original polynomial is written in standard form without any missing powers of x. If they are, put placeholders. So what is this first row I'm going to write? 1, 10, 21. What number goes in the tray? -5. So let's perform synthetic division. I bring the first term down. I multiply. What do I get? I add. I multiply. What do I get? I add. Now, this was the power of x squared, x to the first, x. So that means this is x to the first, this is x. So I now have x to the first plus 5 minus 4 over x plus 5. This is my quotient plus my remainder over my divisor. So again, if I wanted to think about it, I could take my x plus 5 times x plus 5 minus 4, if I wanted to set it up that way, right? I'd have my quotient times my divisor plus my remainder, and that will give me look at that, my dividend. You will see why synthetic division becomes beautiful. So again, we wouldn't be able to use synthetic division here. We would have to use long division. As practice, you can. Now, let me just talk about the remainder theorem. The remainder theorem, if a polynomial f of x, so I've given you a polynomial, is divided by a linear binomial, then the remainder is the polynomial evaluated at that x. Okay, I'm just reading straight through what this is telling me. If you are given a polynomial, so f of x, if you are given f of x, I've been given f of x, and it is divided by a linear binomial, right? I know the corresponding solution would be x equal -3, right? Does that make sense from this example? Miles, does that make sense? I have a polynomial. I am dividing it by a linear binomial. The remainder, what we get, is a result of evaluating the polynomial at this x value. So this is my little c. So if I turn this into a function, and I evaluate my function at that C value, what this is telling me is the result is my remainder. So let's go ahead and evaluate that. So this is 9 minus 30 plus 21. So what is the function evaluated at -3? Is that true? Yes. So I have a solution. Now, could I use synthetic division to test this theory? Absolutely. Why can I use synthetic division? Because I'm dividing by a linear binomial. So that means when I do synthetic division, that remainder should be 0. Because that's what I just showed. I could also do long division and I could see that the remainder is 0. So you might want to do that for fun, for kicks. All right, let's look at the remainder theorem again. If I were to take my polynomial, this quadratic trinomial, let's say I have a function that is equal to that quadratic trinomial. I am dividing by x plus 5. So that means I'm evaluating the function at what x value? -5. And what do I get? And again, I could use synthetic division and I could see that my remainder would be -4. That's it. That's all it's telling you, that I can tell you what that remainder is going to be because I could evaluate that polynomial at this corresponding x value. Now, how does that compare to the factor theorem? Well, the factor theorem kind of puts this all together. It's just common sense, really. The factor theorem says, again, I have f of x that's a polynomial. If I am dividing by a linear binomial, then the function evaluated at that x value equals 0 if it's a solution. If I evaluate the function at that c value, then I also know that that corresponding x minus c is a factor. So this is just really kind of reinforcing the fact that, oops, this is my factor, this is my, oops, that's my factor, this is my corresponding, so this is the solution, this is the factor, right? And we know the relationship between solutions and factors, right? We can go back and forth. So this is just putting it all together. If I know that this is a solution, then this is a factor. If I know that this is a factor, then this is a solution. I know that if I substitute in a solution into an equation, I get 0. Because we also know that those factors, those roots, correspond to what on the graph of a polynomial function? Or really, yeah, polynomial function. The x value of the intercepts. And so what is y? Y is 0. F of x equals 0. So that's really all this is saying. So if I want to know what the remainder is here, how would I go about finding the remainder for this problem? I have a polynomial. If I want to know what the remainder is, what would I do? Beautiful. And if it is a solution, what should I get? There, you've just told me the remainder theorem and the factor theorem. Yeah. But if this is just saying that to get the remainder, I substitute in that value of x. But if that remainder is 0, then it is a solution. If it is a solution, the corresponding factor is that x minus that c value. It's just kind of going in circle. That's why I said it's just kind of common sense, but they have fancy names for. So if I asked you to find the remainder, what would we be evaluating f of x at here? -5. And if I get 0, then it is a solution. If I don't get 0, then I know what the remainder is once I do the division. This is kind of another way for you to check when you're doing synthetic division or long division, which your remainder should be.
-5 would be the solution?
No, if f evaluated at -5 equals 0, then we know x equal -5 is a solution.
But -4 would still be
-4 would still be the remainder. So in this case, we do get 0, right? I believe we got 0 for this one. So yes, this is a factor, this is a solution. The remainder 0. In this case, I think we got, like you said, Blaine, -4. So in this case, this is not a solution. It's not going to give us a root of that polynomial. The remainder is -4. So when x equals -5, I'm at -4 on the graph. When x equals -3, I'm at 0. I'm on the x-axis on the graph here. Right? So this is just telling us points on the graph. Now, let's look at the next example. Let's solve this equation given that -2 is a 0 of the equation. Okay? So I am looking for what? Using the remainder theorem, I need to show that it equals 0 if I substitute in that x value, right? So if you are given this, if this is a 0, then I know x equals -2, right? And what is a factor? Beautiful. And then f evaluated at that -2 should give me 0, right? Because I'm telling you it's a 0. So if I give you an equation, if I give you a function and I give you a 0, then you know this. You know a solution if I gave you a 0. If I gave you a 0, I've also given you a corresponding factor. By the factor theorem, I know that this is true. That if I were to substitute in, well, and by the remainder theorem, that the remainder is 0. The output is 0. So let's verify that. I'm going to go ahead and use substitution. Okay, so what is this going to give me? 2 times what? Minus 3 times what? And what would this be? Plus 22 plus 6, right? So -16 minus 12 plus 22 plus 6, what does that give me?
0.
Aha! It better, right? Now, could I have used synthetic division? Yes. Well, how could I could use this, right? That's a linear binomial. So that's the number that goes on the little tray. So let's verify that using synthetic division. Let's verify it doing long division. We should be able to do all of it. So my divisor is x plus 2 for long division. My dividend is 2x cubed minus 3x squared minus 11x plus 6. Using synthetic division, I would put -2 on the tray, and then I might have 2, -3, -11, 6. So far, so good. I can do it either way. It works either way. Shall we do long division first? Sure, why not? What's the first term in my quotient?
X squared
And where does it go?
above the -3x.
Okay. Is it just x squared?
No, it's 2x.
It's 2x squared. Let's do the multiplication. Okay. If I do the multiplication, I'm going to get 2x cubed. What?
Plus 4x squared. Plus 0. Plus 0.
Well, that's all I need,
Yeah.
right? I'm subtracting. These are gone. And what would be the first term in what's left? Thank you. Do you see that? It's negative 3x squared minus 4x squared. Don't forget to subtract. Then I'm going to bring down this minus 11x. Okay, now let's do this. X goes into negative 7x squared. How many times? What am I multiplying? Okay, let's do the multiplication. So I'm going to get negative 7x squared minus 14x. I am subtracting. This goes away. And what am I left with? 3x. Okay, next term in my quotient. So I'm looking at this and this. So what would be the next term in my quotient over my constant term in my dividend? Oh, I forgot to bring down my little 6. Let's do the multiplication. That would give me 3x plus 6. And I should get a remainder of 0 because we said that was a root, right? We said that was a solution. So it worked. So here I was able to get the quotient. If I multiplied the quotient by my dividend, by my divisor, I should get my dividend, right? You can check that. You can always check your answers to see if you did it right. Let's do synthetic division. Because why would we not? First term, bring it down. Multiply. What do I get? Negative 4, then we add, yes, and we get negative 7. Then we multiply and we get, and then we add, and then we multiply, and then we add, and we better get a remainder of 0 because we said it was a root. Now, look at this. This is, we started with, what was the degree? 3. So this is 2x squared minus 7x plus 3. That's fantastic. That's absolutely fantastic. Is that not fantastic? Isn't that a beautiful thing to see on your first day back after all that craziness last week? Okay, we're going to stop there. We're going to talk about how all this fits into the zeros of polynomial and how we can use these to find roots, all of the roots of the polynomial, and then graph it and talk about whether it's smooth and continuous and what an end behavior looks like, our tails. We're going to talk all about all of that. You do have my math lab. You do have lots of practice problems in the packet as well. You can use the remainder of class. You have 29 minutes. You can get a lot of work done in 29 minutes. Yeah, welcome back. Anybody online have any questions?